Suppose we have a 3 by 3 system of linear equations. Let's look at how we solve for x, y and z using the Gauss-Jordan method. Stick around and I'll show you how to produce an augmented matrix and then manipulate the matrix into reduced row echelon form. The system of equations we're asked to solve is shown on the board. The first step is to create a coefficient matrix by extracting the coefficients of variables x, y and z such that they become the entries in the matrix. This results in a 3 by 3 matrix. Next, we augment this matrix by adding the constant terms. We separate these from the coefficients by using a vertical line. Now we need to perform row operations such that the matrix is in reduced row echelon form. So what is reduced row echelon form? Well, we need to reduce our matrix such that it is in the following form. The row operations we perform produces a series of ones along the diagonal from the top left to the bottom right, and all other entries are 0. Now let's look at what rules we are constrained by when reducing the matrix to reduced row echelon form. Rule 1, we can interchange or swap any two rows. Rule 2, we can multiply a row by a non-zero constant. And rule 3, we can add or subtract any two rows, which can be done in conjunction with rule 2, which enables us to multiply a row by a non-zero constant. Let's now apply these rules and demonstrate the step-by-step technique to reduce our augmented matrix to reduced row echelon form. So for step 1, the first row needs to have a leading coefficient of 1. So this element here in row 1, column 1 needs to be a 1. To achieve this, we can swap row 1 with row 2. So row 1 is here and row 2 is here. So now row 1 becomes 1, 1, 2 and 8, and row 2 becomes -1, -2, 3 and 1. And row 3 remains unchanged. For step 2, we need to get zeros in all other entries for column 1. So that means we need a 0 here and a 0 here. So beginning with this element here, if we add row 1 and row 2, so row 1 being here and row 2 being here, we get 0, -1, 5 and 9. And if we multiply row 1 by 3 and then subtract this from row 3, so row 1 is once again here and row 3 is here, this will give 0, -10, -2 and -14. And row 1 remains unchanged. And for step 3, we need to get a 1 in column 2, row 2. So that's this element here. And to achieve this, we can divide row 2 by -1. So this is row 2 here. So if we divide it by -1, we get 0, 1, -5 and -9. Row 1 and row 3 remain unchanged. For step 4, we need to get zeros in all other elements of column 2. So we're talking about this element here and this element here. To achieve this, we can subtract row 2 from row 1. So this is row 2 and this is row 1. And the new row 1 becomes 1, 0, 7 and 17. And then we can multiply row 2 by 10 and add it to row 3. So row 2 is once again here and row 3 is here. And the new row 3 becomes 0, 0, -52 and -104. And for step number 5, we need to get a 1 in the bottom right of the diagonal. So we're talking about this element here. And to achieve this, we can divide row 3 by -52. So row 3 is here. If we divide this by -52, we get 0, 0, 1 and 2. And all other rows remain unchanged. And for step 6, we need to get zeros in all other entries of column 3. So we're talking about this element here and this element here. And to achieve this, we can multiply row 3 by 7 and subtract it from row 1. So row 1 is here and row 3 is here. So performing this operation, our new row 1 becomes 1, 0, 0 and 3. And then we can multiply row 3 by 5 and add it to row 2. So row 2 is here, and row 3 once again here. The new row 2 becomes 0, 1, 0, and 1. And row 3 remains unchanged. So now we have the matrix in reduced row echelon form. And each of the columns represents a variable. So column 1 represents x, column 2 represents y, and column 3 represents z. So if we look at row 1, we can see that we have 1x, 0 y's, 0 z's, and this is equal to 3. So this means that x is equal to 3. And looking at row 2, we have 0 x's, 1 y, 0 z's, and this is equal to 1. So therefore y is equal to 1. And finally, looking at row 3, we have 0 x's, 0 y's, 1 z, and this is equal to 2. So therefore z is equal to 2. So the solution to our 3x3 system of linear equations is x equals 3, y equals 1, and z equals 2.